Hello everyone, my name is Neil Thomson. I'm with the Department of Civil and Environmental Engineering at the University of Waterloo. The focus of today's lecture is on in situ chemical oxidation, or ISCO. What I'll be speaking about over a few segments here is what is ISCO, what are the advantages of ISCO, ways to deliver the compounds or the chemical oxidants into the target zone. Following that, I'll speak about the various involved chemistry with all of the chemical oxidants that are applied now. Talk about an important area that's called aquifer-material interactions. Talk about the early lab results, and then speak about the idea of enhanced mass removal, and then finally speak about the outcomes or the prognosis for treatment. As we have heard so far in this course, the problem involved a source zone where we have the non-aqueous phase liquid and a plume or a dissolved phase off the plume. The goal of ISCO is to treat the non-aqueous phase liquids or to treat a non-mobile sorbed phase. It's clear that in this world, trying to treat a dissolved phase with the injection of a dissolved phase becomes rather problematic, and by and large can be done, but some special considerations must be made. So what is ISCO? Well, it involves the delivery of chemical oxidants into the subsurface to transform the contaminants of concern and reduce their mass, mobility, and toxicity. So the general result is to react or break down the contaminant of concern. Now it involves more than just electron transfer. It can also involve hydrogen atom transfer, a hydride transfer, or a oxygen donation process. It involves any reaction that converts one compound to a different oxidation stage. The oxidants that are used are on this slide here. So all of the range of possible oxidants, there are 4 oxidants that have been promoted and used. Hydrogen peroxide is probably the first one, and it is now classified in this area of catalyzed hydrogen peroxide propagations. And that involves a hydrogen peroxide either mixed with a ferrous iron, a chelated iron, or perhaps the natural iron that is present to create a reaction. There's also a solid peroxygen that is similar to a solid phase hydrogen peroxide. Ozone is a gas that is a very powerful oxidant, and it's applied very much in the same mode as in situ air sparging. If the zone has been pre-flooded with hydrogen peroxide and you inject under that zone through an air sparging process ozone, you end up with the peroxone process. Perhaps the most widely used oxidant is permanganate, and the newest oxidant around is persulfate. That's a very rich chemistry involved and can be activated by a range of approaches. The reactive compounds include benzene, toluene, ethylbenzene, and xylenes, or the BTEX family, MTBE, a range of chlorinated solvents including ethenes and ethanes, a spectrum of polycyclic aromatic hydrocarbons, or PAHs, some polychlorinated biphenyl isomers, chlorinated benzenes, some organic pesticides, phenols, and some type of, or some forms, I should say, of explosives. So the upside or the sales pitch involves when you inject a chemical oxidant in the ground, you have in situ mass destruction at the place of reaction. You will enhance the mass transfer, and that means you can actually speed up cleanup. For some reactions, they end up with a non-toxic end products such as H2O, water, and carbon dioxide. It's a fairly rapid treatment process within the realm of the time frames for groundwater flow. It's a relatively simple process and low cost. How do we get the reactants in the ground? Well, that becomes extremely important. How do we actually flush the source zone? Well, one of the first ways that was applied is a two-well dipole flow system, where one well is an injection well and the other well is the extraction well. The extraction well would extract the groundwater fluid, including the oxidant, augment above ground, and then re-inject that augmented fluid back into the well. That way you can maximize the oxidant concentration within the source zone. You can expand that to a standard oil field 5-spot production platform in which you inject in the center well and extract out of the 4 peripheral wells. For a case where you don't have access through a vertical wells, you can use horizontal wells that are long screen wells that act as a line source and sink to flush between one horizontal well and the other horizontal well. Again, trying to increase or maintain an elevated concentration within the target zone. But perhaps of all those ways, perhaps the most widely used ways is through a permanent or a temporary injection points, where you have one well, you inject only, and there's no extraction phase at all. So something like a geoprobe rig could be used for a temporary injection point. Sometimes in a geoprobe rig, you inject high, and as you advance the point down, you inject, and that's called a top-down injection process. The alternative is you push the rod all the way down to the bottom of the target zone, and as you pull up the rod, you inject. Of course, that's called the bottom up. Now, if you have complete access to the area and you have enough financial support, likely the best way is to take a giant auger and add in the oxidant and have what is called soil mixing, which you completely mix the oxidant within the impacted soil zone. ISCO has grown dramatically over the last 20 years. There have been over 300 field applications of ISCO, and EPA has a really good site, a clue-in site, where various consultants and others have uploaded their case studies. I should say they have selectively uploaded their case studies, so what you'll find there is probably the most successful case studies around. Most, I would say the majority of applications have involved hydrogen peroxide or catalyzed hydrogen peroxide, ozone permanganate, and persulfates. By and large, the most common deliver approach is through a direct push probe or drilled wells. And there has been a range of other possible application approaches used. Well, that concludes the opening segment on ISCO. The next segment talks about the chemical reagents used and a little bit more about the involved chemistry. Thanks a lot, and that's all for now. Bye.